So let us discuss the first algorithm of pressure-based numerical method, that is nothing but the segregated algorithm. All right. So it is quite simple. It is not a big rocket science over here. Just try to focus and understand. Now the pressure-based solver uses solution algorithm where the governing equations are solved sequentially. So this is more important over here, that the governing equations, whatever we have considered in our model or the simulation, those equations are solved in sequence. That is the reason segregated is the name that is given to them, right? Given to this algorithm, right? Now, because these governing equations are non-linear, as I've mentioned you previously, those equations are non-linear and coupled, the solution loop must be carried out iteratively in order to obtain a converged numerical solution. So we have already read about this thing. Now, in the segregated algorithm, the individual governing equations for the solution variables, that is the velocity, the pressure, the temperature, and the turbulence are solved one after other. This is what is happening in segregated algorithm of the pressure-based numerical method. What's happening is whatever governing equations we have, which are used for solving certain variables. Okay, what are the variables? Variables are the unknowns that we are finding from the solution or the simulation. Okay, now we have this u, v, w over here. These are nothing but the velocity fields in u, v, and w direction. Okay, that is x, y, and z direction. Then we have the pressure, we have the temperature, and we have this turbulence, k and epsilon. And what's happening is these equations, which are objected to solve the solution variables, are solved one after the other. That is what is written over here. So they are solved one after another. Each governing equation, while being solved, is decoupled, right? I mentioned you that the equations are coupled. Now each governing equation is one by one decoupled or segregated from the other equations. That is why its name is given as pressure-based segregated algorithm. The segregated algorithm is memory efficient since the discretized equations need only to be stored in the memory one at a time. And I believe it doesn't require a lot of RAM when we are utilizing the segregated algorithm, because the equations are stored one by one. The first equation is considered, for example, this is the momentum equation, u, v, w direction. Okay, so we will be having the u momentum equation in the RAM or in the memory. Then after that we will be having the v, then w, then the pressure equation, then the temperature, that is energy equation, then the turbulence equations, right? So one by one, one after the other, we are decoupling them and we are solving them, right? That is what is happening in the segregated algorithm. However, the solution convergence is relatively slow, and the amount of time required for converging, okay, I mentioned in the previous video that convergence is nothing but to ensure that all the values what we got, right, those values are below a benchmark value, right? And in the segregated algorithm, the time taken to converge or time taken for that values to fall below the benchmark value will be higher, because we are solving the equations one by one. So it takes a lot of time for solving this particular form of case, right? And what's happening, we will just see the steps one by one. We also have a table being created, flowchart being created over here, but let us just read over here, then we will just go to the flowchart. All right, now what is the first step? The first step is we are guessing the fluid properties. Example, the density. We are updating the fluid properties, that is the density, the viscosity, the specific heat, and the turbulent viscosity based on the current solution. What is happening is when we are entering the boundary conditions, and depending on the boundary conditions what we have assigned to our domain or the model, a kind of guess values are being considered by the software. Okay, the software guesses some values, and those values or those properties are updated at first. So that is the first step in the pressure-based segregated algorithm. With those values what we have, we are trying to solve the momentum equations one after the other. Okay, and the momentum equations one after the other using the recently updated values of pressure and phase mass fluxes. So whatever values we have guessed over here, with those values we are solving the we are solving the momentum equation. Now momentum equation is nothing but in three directions, that is x, y, and z direction. All right, So this is nothing but the velocity equation. Clear? Then the next third point is, with this values what we got with the values of velocity from the momentum equation, we are solving the pressure correction equation using the recently obtained velocity field and the mass flux. So at this step we are getting the velocity field because we are solving the momentum equation, and we're getting the mass fluxes as well, right? So with this values what we have, we are solving the pressure equation or the pressure correction equation, that is utilized with the help of continuity equation. And the first step is nothing but we are correcting the phase mass fluxes, the pressure value and the velocity field using the pressure correction equation obtained from the step 3. Now you can see that we have considered a guess value at first. With the help of guess value we are solving the momentum equation to get the velocity field. We are utilizing this velocity field to solve the pressure correction equation, and we are obtaining the pressure values and the mass flux values, and based on this values we are updating this values over here. Okay, initially whatever we have guessed, now those values will be replaced with the updated values. Okay, that is what is happening over here. Then after that we are solving the equation for additional scalars, for example the turbulent quantities, energy equation, species, radiation density, etc. So all these things are dependent on the objective. For example, if we have some radiation involved in our model, then we will be utilizing the radiation equations. If we have the species, that means for example if you want to model water vapor, okay, or if you want to model combustion, then we will be having the species equation being required. If you want to model the temperature, if you want to see the temperature variations in the domain, then we will be considering the energy equation as well. Otherwise, I mentioned you that energy equation is not required always in the pressure based solver. We can just go without the energy equation as well, because it might not be needed for us to solve the temperature field in that particular case. If we require, then only we will be selecting the energy equation and including it in the model, so that it gives us the values what it is required to give us. Whereas in the density based solver, energy equation is compulsorily activated, right? So after attaining the updated values of mass fluxes, pressures and velocity, we are next moving to the solution of next type of equations which are unknowns for us, right? Those are nothing but the energy, species, turbulence, etc., right? Now after solution of this, we are getting certain numerical values. We are checking the numerical values and we are seeing whether those values are below a benchmark value. If it is below the benchmark value, then we can say that the solution is converged. Otherwise, we are just going back to the beginning of the complete path, and we are considering the last updated values, and we are again solving the velocity equation. Then with this velocity flow field, we are solving the pressure correction equation, and we are again updating the next set of values of the mass, flux, pressure, velocity. Then we are solving the energy equations, and again we are checking whether the values are below the benchmark value. If it is below the benchmark value, the solution is converged. We can stop at that time. Otherwise, whatever were the last updated values, we will just consider them again over here, and again we will solve the velocity equation, that is the momentum equation, and we will then solve the pressure correction equation, and we are getting some again updated values. And after that we are solving the energy equations or any additional equations involved in the mathematical model and checking whether they are below the benchmark value. So this is how the iterations are happening, and you know, you'll be the iterations are in millions, sometimes are in thousands sometimes. Okay, it depends on the case, it depends on the domain size, it depends on the number of grid elements you have in your CFD domain. So all those factors all those factors basically are considered, and you will be having the solution converged after the span of time. Okay, so all these things cannot be done manually. Okay, you can just imagine this is a very difficult task and it is not possible for us to do. The computer is required, a computer program is required. That is how the solvers are made for. Clear? Now in the next video we will be discussing about the next algorithm, that is the coupled algorithm. So this is a very simple thing, it can happen very quickly. So let us move to the next video.